Alright, hello students, welcome back to another lecture video on for ComSci 125 operating systems. So we are in the CPU scheduling chapter and we just finished the round robin CPU scheduling algorithm. So we move on to the next algorithm, which is priority scheduling. Now in priority scheduling, the idea is to assign a priority number, which is essentially an integer, and associate that priority number to a process. And what happens is the CPU is allocated to the process with the highest priority. Now by convention, or actually it differs among operating systems, the smaller the priority number, the higher the priority. And priority scheduling can also be preemptive and non-preemptive. When you say preemptive, if a process is running on the CPU and a new high priority process arrives, then the one that is currently running on the CPU is preempted or taken out of the CPU because a higher priority process arrived. On the other hand, the non-preemptive, even though a high priority process arrived, the currently running process on the CPU will complete its time slice on the CPU. So we can actually think of SJF as a specific instance of priority scheduling, where the priority is the inverse of the predicted next CPU burst time. So it's you can think of the that value, the CPU predicted CPU burst time, and take the inverse of that, and that will be the priority of a process. Now the main problem with priority scheduling is starvation, especially if you have preemptive scheduling. Why? Because low priority processes will not have the chance to execute on the CPU because they will always be preempted by higher priority process, especially in a system with a lot of high priority processes are coming in. So to solve that problem, a solution called aging is used. This means that over time, low priority process, the priority of low priority process will be adjusted, will be increased, so that they will have the chance to execute on the CPU. So that's the trick to solve the problem. So let's have an example of priority scheduling. So we are given a set of processes P1 to P5, and also their burst time and the priority. If we're going to write the schedule for this set of processes, so we look at the priority numbers. We said that the lower value for priority indicates a high priority process. So when we write the schedule, this is how it will look like. So first we have P2, which is the first to execute. It consumes 1 burst time. Then we look at the next priority number, which is 2, and it will take 5 time units to complete. And then next is P1, because its priority is 3. So we have this schedule, and so on and so forth. And we will see that the average waiting time is 8.2 time units. Okay, so a common question will arise: what if processes have the same there are processes that have the same priorities? So how do we schedule them? So usually to schedule these processes, we combine priority scheduling and round robin. So given this set of processes, again we have 5 processes, their burst times and priority. So what we do is to run the process with the highest priority, process with the same priority, run round robin. So let's say we have a queue of 2. So this is the schedule. So first we start with the highest priority process, which is process 4. And it eats up 7 time units of the CPU. Then we look at the next process to run, and we observe that 2 processes have the same priority, 2 here. So how do we go about scheduling this? So we use the round robin. So first we schedule P2, so 7, 8, 9, so it's until completion, and then P3. So again our queue is 2, so we only allow P2 to execute 2 time units. And then we also run next P3, also 2 time units, so 9, 10, 11. And then still these are higher priority processes, so we have again P2, P3, and then P2. So until this point P2 is done already, so P3 will take this remaining time. And then after that we also have 2 processes, P1 and P5, that have the same priority. So again we use the round robin. So we start with P1 first, 2 time units, then P5, 2 time units also, until all of their burst times are completed. So I leave the computation of the average waiting time to you. So this is how to resolve processes with the same priorities. Right. So it's also interesting that we can have what we call multi-level queues. So traditionally, in the discussion of the previous scheduling algorithms, we maintain a single ready queue. But it's also possible to have multiple queues depending on the priorities of the processes. So we can have something like this. We can have a queue for processes with priority 0. Then we can have a queue for processes with priority 1, etc., up to n. So normally modern operating systems implement these types of multi-level queue or run queues. Actually in Linux, in the early schedulers for Linux, so they maintain different priority queues, and the scheduling happens first by scheduling processes on the highest priority queue. And the prioritization can actually be based on the type of the processes. So for example, you can have a queue for real-time processes, a queue for system processes, a queue for interactive processes, and a queue for batch processes. In modern operating systems, these are called scheduling classes actually. So that's another way to look at it. And in the original multi-level queue, once a process is assigned to a particular queue, they cannot move to different queues. But again, there might be starvation in this scenario. So what if we allow processes to move from one queue to another? So we can actually do that in a multi-level feedback queue, wherein a process can move between or among the various queues. And the multi-level feedback queue scheduler is defined by these parameters. First, how many queues are there? Then, what scheduling algorithm will be used for each queue? And there should be a mechanism or a method to decide when to upgrade or downgrade a process, or to upgrade or to move a process from one queue to another. And then the method used to determine which queue a process will enter when that process needs service. Right? And of course, to prevent starvation, we can also implement aging. Okay, so here's an example of a multi-level feedback queue. Here we have, so considering the previous parameters, number of queues, we have 3 queues. Then the scheduling algorithm for each queue. So for the first queue, we have a round robin with quantum of 8, and the second queue also round robin with 16 time quantum, and the last queue is FCFS. And then the next one is to upgrading and downgrading process. So a new process enters queue 0 initially, okay, say P, which is served in round robin. When it gains CPU, the process receives 8 milliseconds. If it does not finish in 8 milliseconds, then that process will be moved to second queue, Q1 here. At Q1, the job is again served in round robin, but this time we have 16 time units. And if it's not yet completed, then it will go to the first come, first serve queue. So that's the idea of the multi-level feedback queue. Okay, so those previous discussion pertains to processes, right? And with the assumption that one process has one thread. But in reality, modern processes actually have multiple threads, and the scheduling actually happens at the thread level instead of the process level. And recall that we also have a distinction between user level and kernel level threads. When we say user level threads, these are the threads managed by the thread library like pthread, and then kernel thread are the threads that are managed by the operating system kernel, and these kernel threads are actually those that are executed on the hardware. So going back to our previous discussion on threads, for example, so we have the kernel here and we have the user level here, and we discussed different thread models like one-to-many, many-to-one, etc., or mixed, right? So when threads are supported, threads are scheduled, not processes, and we have many-to-one or many-to-many models. And the thread library schedules user level threads to run, or sometimes on lightweight processes. Recall in our discussion that we can have a lightweight process here to actually schedule the threads to have a mapping between kernel thread and user level thread. Now actually in Linux it's simplified because Linux uses a one-to-one mapping, meaning one kernel thread to one user level thread, so it's much easier. So when threads are, so let's say you have a thread library pthread, and the scheduling is happening at the user level, we call that process contention scope. Okay. So the idea is because let's say this is a process, okay, and the contention will happen within the scope of the process, and this can be done by the programmer. Now, in the system contention scope, that means that the competition or the scheduling will happen in the entire system, all threads in the system. So we have other threads here from other processes, so they will contend with all the threads in the system. So that's the idea, the difference between the two. And in Linux, it's usually system scope. Okay. And pthread allows an API to, if the operating system kernel supports it, to specify whether to use a process contention scope or system contention scope. Right? So again, when I say process contention scope, the scheduling will be done on this context only. But if you have a system contention scope, you have to compete with all the threads in the system. So here's an example of pthread code, C code that uses pthread to determine the thread scheduling scope. Okay, and it simply illustrates what functions are used to determine the thread contention scope by using get scope and set scope. Okay, so far what we've been discussing is scheduling in single processor systems. Now, of course, modern systems actually have many processors, and it actually becomes more complex if you have multiple processors or CPUs. And you can actually look at different architectures, like you can have scheduling in the context of multi-core CPUs, and given that we have multi-core CPUs, we can actually have multi-threaded cores, and we can have non-uniform memory access systems, and we take a look at heterogeneous multiprocessing, like in cell phones. I recall we'll talk about that cell phones later, because cell phones actually use this heterogeneous multiprocessing. So let's start with how to go about multiprocessor scheduling. So at the very least, the main subsystem or module in an operating system that implements the scheduling process is the scheduler, CPU scheduler. And to be able to accomplish its task, it maintains a ready queue or a run queue, which contains a list of processes that are ready to run. Okay. Now, in the case of multiprocessor systems, there are actually two ways to do that. One is asymmetric multiprocessing, and the other one is symmetric multiprocessing. In asymmetric processing, what happens is that we have a single core that is dedicated for maintaining a ready queue. Okay, and this particular dedicated processor is the one responsible for accessing this data structure. Somehow there is a master processor that does the job. Okay, so however, a better approach is to have a symmetric multiprocessing wherein each processor is self-scheduling. Okay, which is traditionally what we have, and not traditionally, which is what we have right now in modern processors. So the idea of symmetric multiprocessing is that they can either share a common ready queue and then or they can have a per core or per CPU run queue or ready queue. So this is how it looks like. So we have, let's say, n cores here, and we have a ready queue where each core will pick the task that will execute on that particular core. Or it can have separate queues of tasks for each core. Okay, so we have advantages and disadvantages of each approach. Okay, so what are the advantages? If we are sharing a single ready queue, then we can have a race condition problem here, okay? Because if each core is self-scheduling, they will need to have exclusive access to this shared ready queue, and that will require some locking mechanisms, as we've discussed before, and it's quite expensive to maintain, so it will affect the performance. Okay, so a better approach is to have a per core queue, so that there is no this core can only has exclusive access to this particular queue only, so it doesn't have to contend with the other cores when selecting or running tasks. So in general, it's better to use a separate run queue for each core. Okay, so recent trend is to place multiple processor cores on the same physical chip, and so that's basically the idea of multi-core processors, and it's faster and consumes less power. And it's also possible to have multiple threads per core. Why do we need to have multiple threads per core? Well, it takes advantage of memory stall to make progress on another thread while memory retrieve happens. So for example, we have this is the processor or the core. So we have the core. So we have a compute cycle and then the memory access cycle. Now this memory access cycle will actually make the CPU or the core idle. It's doing nothing. It's waiting for the memory load or store to complete. Right? So this is a wastage. So it's better to have hardware threads. Right? So each core has more than one hardware threads, and if one thread has a memory stall, then we switch to another thread. So let's say this is thread 0, and then there is a memory stall here. So we switch execution on the other thread. Okay, so let's take a look at an example. Let me fix this. Okay. Okay, so I have this so as you can see, okay, so this is the machine that I have here. Okay, so I have 32 cores, and I have 2 threads per core. This is what I am referring a while ago. And we have sockets, okay, cores per socket, and then we have 8 cores per socket here, and then we also have NUMA nodes here. So this is the importance of having hardware threads per core. Okay. So going back, so that's the idea. Okay. So here is how the logical view of a modern processor will look like. So we call this the socket. Let's call this. So in the socket. So how many cores per socket? We have 4 cores per socket here, and we have 2 threads, 2 hardware threads per core. Okay. So chip multithreading assigns each core multiple hardware threads. Intel refers to this as hyperthreading. And on a quad-core system with 2 hardware threads per core, the operating system sees 8 logical processors. So what happens is this is 1, 2, 3, 4, 5, 6, 7, 8, and the operating system will actually see that as 8 logical CPUs. Okay. So you see here again the importance of the operating system as providing an abstraction, okay, for this somehow complicated but a high performance hardware. And as a result of this multi-threaded multi-core system, we can actually we now actually have 2 levels of scheduling. Okay. So we have scheduling thread level at the user software threads, and we also have the scheduling on the hardware threads, okay, as shown here. And then we have the processing core here, okay. So this software thread, okay, so actually you can think of this as the kernel threads, because this is actually where the kernel will run these software or user level threads. Okay, so great. We have again, the purpose of multiprocessors is to improve performance, increase throughput, right, etc. Now, sometimes we also have a concern about efficiency. Okay? So in multiprocessor scheduling, in addition to determining which task or processes to execute on which core, there should also be it should also integrate load balancing. Okay? And the idea of load balancing, of course, is to keep all the CPUs busy. We don't want to overburden a particular core with all the tasks. Okay? So load balancing attempts to keep the workload evenly distributed, and there are 2 ways to do that. I think we've mentioned this in the introduction before. Push migration, wherein there is a process that checks the load on each processor, and or the process checks the load on its processor, and if found, push tasks from the overly loaded CPU to other CPUs, or pull migration, wherein idle processors pull waiting tasks from the busy processor. Okay, so again, the idea is each processor is self-scheduling. Okay, so we have a scheduler here, right? A scheduler that selects which of these tasks will run next on this core. So we have the concept of processor affinity. Okay, so when a thread has been running on one processor, right, the cache contents of that processor stores the memory access by the thread. Okay? And we refer to this as a thread having affinity for a processor, or processor affinity. So remember that if this is the socket, okay, and we have threads here, in terms of storage, usually we have caches here. Okay. So cache, and we have core here. So when executing instructions, the data are fetched from the cache first. Okay, so if a process or a thread is running on this core, all the data that it references most likely will be stored on the cache on that particular socket or processor. Okay, so this calls the thread. Okay, so thread, hardware thread. Okay. So that's the idea. And load balancing may affect processor affinity, as a thread may be moved from one processor to another to balance load. Yet that thread loses the contents of what it had in the cache of the processor it was moved off of. So let's say we have, again, let's just illustrate this. We have these two sockets. So socket 1, we have socket 2, then we have hardware thread 1, let's say 2 hardware threads, and if this thread, for example, is running on this socket, the data it uses in its execution will be stored in this cache. Now at some point, a decision to load balance is made, and this thread is moved to this thread. So the data that was previously used by this thread are stored in this cache, and since it is moved to this new socket or a different hardware thread, then it has to replenish the cache with the correct data and invalidate whatever is in this data. So again, that will affect the performance of the process, because it has to repopulate, or it has to fetch the data again from the main memory and repopulate the cache. So that is called processor affinity. And we have soft affinity, wherein the operating system attempts to keep a thread running on the same processor, but no guarantees. Or it can be a hard affinity, okay, wherein the process is set to run on that particular processor. So let me show you an example. So let's see. Let's check where a processor core is running from. So let's have an example of that. The VM. You can see the VM. I need some guide to do this. Okay, so we have this code. Okay, this command line to determine the processes running on a given core. So our our machine here has only one core. So these are the processes that are, since we only have one core actually, so we cannot see this. So I think it's better if we use the this one. So the host OS. Check if we can paste. No, we can't. So let's take a look at processes. And let's copy this line here. So this will show us which processes are running on core 1. So we have these processes running on core 1. How about core 2? So these are the processes that are running on core 2. How about core 32? So no processes are running on core 32. So this is core 32, so empty. So you see here the load balancing that is happening. Okay, so to further illustrate, let's create a program. You can see my terminal. Then should we do we can run this code. Just put this. No, we can't. So we just open the terminal. Okay, so we run this. So let's check. Let's see which processor this particular process is running. So it's actually running on this is the processor number. Okay, so you will notice that this particular process is moving from one logical processor to another. So it is not fixed because of the load balancing that is being implemented. So this value here changes. Okay? So we have the concept of processor affinity. So we can actually, in Linux, we can actually force this process to stick to a particular core, and you can do this using the task set command. So that if we want to run this particular process to a specific core, let's say core 16, okay, we can do that using the task set command, and then you will notice now that we've fixed the location of this particular process. We've specified explicitly where to run this particular process. Okay? So if we look at HTAP, you will see that 16 here, this is core 16. Part of the statistics here is from the loop process is running on this particular processor. So if we want to specify multiple cores to execute this process, let's say 20, you can do that, and you will see that the scheduler should be, or I might have made the wrong syntax, but the scheduler should be able to, so I think I made the right syntax, but see the idea. So if you want it to run on core 20, you can do that, and you see the result. Okay, so that's the idea of processor affinity. We can tell or we can bind the process to run on a particular core. So non-uniform memory access. So if the operating system is MUMA aware, it will assign memory closest to the CPU the thread is running on. Right? So if we look at the statistics, stop this, or the CPU specs, you can see here the nodes that are NUMA. So the scheduler can determine or can select the appropriate core, right? So that it can optimize the memory access in case you have non-uniform memory access. Okay, so we'll skip real-time CPU scheduling, but the main idea is scheduling will have different requirements depending on the need, and an essential category of devices or approach is called real-time scheduling, wherein there are strict constraints with regards to time, because a delay will actually can cause harm or even death, for example. Okay, for example, you have a car braking system, okay, or usually in embedded systems they have real-time scheduling. But we'll skip this section of this chapter. So we move on now to so example operating system. So we focus on the Linux scheduling scheduling. Okay, so over the years, the Linux has evolved, and different scheduling algorithms have been developed for it. Prior to kernel 2.5, it ran a variation of the standard Unix scheduling algorithms. And when it moved to version 2.5, it implemented an O of 1 scheduling algorithm. What is this O of 1 scheduling algorithm? It is a preemptive, priority-based scheduling algorithm. It has two priority ranges, time sharing and real time. So usually this is the default for desktop use. Real time ranges from the priority, these are priority numbers. So for real time, the value of priority is from 0 to 99. And a nice value from 100 to 140 is mapped into a global priority with numerically lower values indicating higher priority. So this is the user's way to indicate priority, but internally there is a corresponding value or conversion that happens. Higher priority gets a larger quanta or time slice, okay? Or a higher number of time or amount of time to spend on the CPU. The task runnable as long as time left in time slice. So again, in Linux, processes are called tasks, okay? Or threads actually. So the threads are runnable as long as there is time left in time slice. If no time left, so it's called expired. And it will not be runnable until all other tasks use their slices. So this is actually where the performance of the O of 1 scheduler was scrutinized, because of this process. That once a process or a task time slot is expired, it will have to wait for other processes to finish. So it's not really good for interactive processes. All runnable tasks are tracked in a per CPU run queue with a structure similar to the ready queue actually, which are actually two priority arrays. We have active and expired, and the tasks are indexed by priority, and when no more active arrays are exchanged, okay, worked well but poor response time for interactive process. So the idea is you have something like this okay. So these are active and these are expired. So the processes or the task will queue on this. Let's say this is 100. Right? So the scheduler will select one process, execute that until time slice, and then place that on this expired queue, and then once everything here is done, it swaps this expired and active. So that's the idea of the O of 1 scheduler. So why O of 1? Because it simply selects the next available process on that is present on the active queue. So, and also it uses a bitmap to easily determine which process is available or which queue has available processes to run. So in the Linux kernel version 2.6.23, a new scheduling algorithm, which actually the default algorithm that is being used now in Linux, is called the completely fair scheduler, or CFS. It has several scheduling classes. So each has a specific priority. The scheduler picks the highest priority task in the highest scheduling class. So rather than a quantum based on fixed time allotments, it's based on the proportion of time. So the idea is to actually make it fair for all the processes. And there are two scheduling classes. We have the default and the real time. So of course, if you're using a desktop Linux or Ubuntu, for example, you'll have the default class. So how does this work? So again, we have a quantum or the time slice, and this is calculated based on a nice value from -20 to +19. The lower value is higher priority. It calculates a target latency, which is the interval of time during which tasks should run at least once. Okay, so again, there's a mechanism to do this so that it's actually is used to make it fair to all the processes. So the target latency can increase if the number of active tasks increases. So it considers the number of active processes. And the CFS scheduler maintains a per task virtual runtime in a variable called runtime. So it's actually a runtime, but rather it's an integer or some value that is incremented, which every time a process runs on the processor. Okay. It is associated with a decay factor based on the priority of tasks. So the lower the priority, the higher the decay rate. And the normal default priority yields the virtual runtime equal to the actual runtime. To decide the next task to run, the scheduler picks the task with the lowest virtual runtime. So that's quite a lot to absorb. So, but the idea is to make sure, okay, so to make sure that somehow approximate that all the processes in the system, okay, active tasks will have a chance to execute on a target latency. Okay, and it has some computations, but I will just leave that to you. There's a reading on the details of the CFS. You can do this by reading the Understanding the Linux Kernel book. Okay, so the details of this scheduling algorithm is discussed there. So in terms of performance, okay, one interesting performance advantage of CFS is the use of the red-black tree. So in ComSci 123, you probably heard of binary search tree and AVL trees, which are height balance trees. And red-black tree is one of these data structures. Okay, each node in this red-black tree, the value is, the key is actually a priority queue. So the value is the V runtime. So what happens is when a process is created, okay, it is given a minimum runtime, V runtime, and then it is added to this red-black tree, and the scheduler will simply pick the leftmost as the next process to schedule to run on the CPU. After a while, the VRAM time will be incremented and it will be added back again to the red black tree for possible selection in the next iteration of the scheduling decision. So in a way, CFS actually improved the performance because all tasks are actually somehow given equal opportunity to use the processor. Okay, so this is for real time, so we ignore this. Okay, so it's also possible for Linux to have to be NUMA aware, so it can create scheduling domains. Okay. So the goal is to keep threads from migrating between domains. Okay, so that again, so that they will not to improve performance. Okay. Because we have NUMA or NUMA. Okay, so let's take a look at some examples of the scheduling in Linux. So let's just go back to our VM. Okay, so the top command will tell us the processes that are running. Okay, so as you can see, there are a lot of processes running on this particular Linux in our VM. And I started the process here, the calculator process. So you can see the is actually using CFS scheduler because so it's using already version 5.4.0 version of the Linux kernel. So it's assumed that we're using the CFS scheduler here. So let's say I use some computation, run some computation, and you will notice that the calc process will take up some CPU and some memory whenever you perform some computations. So you will see that it will appear on the top of the list, okay? Because this is sorted on the CPU and memory. Okay, so let's take a look at so in the top view, we have nice and we have priority here. So I mentioned in the slide, okay, I mentioned in the slide that okay, the quantum is calculated based on a nice value from -20 to +19, and the priority actually is computed based on this nice value. So if you look at the output of top 9, we will see that, for example, if we look at the calculator, okay, so if you look at the GNOME calculator, okay, its priority is 20 and its nice value is 0. Okay, so we said that the lower the value is, the higher the priority. So we can actually lower the priority of the GNOME calculator by renicing it to, let's say, if we renice it to 0, to 10, for example. Okay. Let's see what will happen. So you notice that the priority is decreased. So we said that the lower the value, the higher the priority, the lower the value here. So if we can revise it, let's say -10, okay, so priority is 0. So okay, so the calculator should now have a higher priority. Okay, so by default, what is the priority assigned to a process? So I have here a process loop, okay, and then okay. So by default, when a new process is created, remember that in Linux, a process is created using the fork system call, and that new process will be given a priority of by default 20. Okay, as you can see here, this is the process, but we can actually run this with a different priority, and you can see here that we have a higher priority because we increase the niceness of this process. Okay, so that's how we control the priority of the process. Okay, so that's Linux scheduler. So to summarize, Linux uses CFS and is a fair share scheduling system, and it does this by taking into consideration the number of processes that are running in the system. So okay, so I'm going to skip Windows scheduling and Solaris, and we go to the last section, which is algorithm evaluation. Okay, so let's say you have a research project and you are asked to evaluate different scheduling algorithms. How are you going to approach that? So there are several ways to do that, and the first step, of course, is to determine the criteria and then evaluate the algorithms. Right? So let's say if you want to support interactive processes, right, or high server loads, etc. So you want to increase throughput, or you want to decrease the average waiting time, etc. So you have to set the criteria. So the first is deterministic modeling. Okay, so this is what we actually did in the examples when we presented some computations for the different scheduling algorithms. So for example, we are given a set of processes and their burst time, and then to compare the different algorithms, we perform some computations by computing the waiting time, etc. So this is what we did in the previous discussions. We can also have queuing models, which is actually from statistics. Okay? So we use some we understand the distribution of the CPU and I/O burst and use probability to determine the distribution, and then we compute some variables and use a formula to determine, for example, the average wait time. For example, we can have the Little's formula, where we are given the average queue length, the average waiting time, then we can actually compute lambda here, which is the average arrival rate into queue. So we can have this example. For example, if on the average we have 7 processes arrive per second, and normally 14 processes in queue, which is the queue length, okay, then the average wait time per queue is simply n14 divided by the average arrival rate, 7. So we have 2 seconds. So it's a formula. Or we can run some simulations like what you did in the lab, okay, when you program some scheduling simulations. So simulations can be more accurate. Program model of your system, a variable clock, okay? And the main issue with simulation is how do you provide, or where do you get the input to the simulation. There are several ways to do that. You can have synthetic inputs by using a random number generator, or you can use some distributions to generate a set of inputs, or you can actually obtain what you call traces, or traces of runs, and then use that as input to your simulation. But however, to obtain that will require some instrumentation and might be difficult also to obtain. So most people would rely on random number generations and distributions using mathematical formulas. For example here, so you have different traces here. So CPU 10 burst times, IO 213 burst times, and then you feed that to the simulation, and then you calculate some statistics. So that's basically that's one thing you can do. Or the last one is to implement it. Okay? So implement the algorithm that you developed. Use it in the patch the Linux kernel with your new algorithm, or probably implement a kernel module that implements your new scheduling algorithm. So that's one way to do that. And of course, it might be difficult to do, or it might be easier to do. In the case of Linux, currently I think a lot of people are happy with the CFS, but I suppose in Google data centers, for example, or in Facebook data centers, they have customized Linux kernels with customized schedulers tailored to the specific workloads of their data centers. Okay, with that, I end chapter 5, which is CPU scheduling.